All right, welcome everyone to the last day of this conference, discussion meeting. The first speaker for today is going to be CM Chandrasekhar, who will tell us about simulating quantum many-body systems using photonic qubits. Okay.
So thank you very much for the invitation. And the title of the talk says many-body system using photonic qubits. So for me here, many-body would be 1, 2, and many. I'll not be talking more than 3 or 6 qubits, but at least it sets a ground how for like the way of or the way you can use qubits to realize many-body system. So simulation, or when we talk about quantum simulation, so it mainly deals with looking at some quantum system and what are the ways I can prepare a similar state and look at the dynamics or model dynamics which mimics the real system and make some measurement. So the whole idea would be like to harness a controllable quantum evolution in one quantum system to simulate another inaccessible complex systems. So there are a lot of complex systems in nature. It can be physics, chemistry, biological, or the systems can be a mixture of quantum dynamics and have some environmental effects. So there are huge samples of them. So it's one of the main objectives for quantum simulator. So the other part is like, if I'm looking at an exponential scaling resources needed, if I'm looking at simulating some system, I need an exponentially scaling resource in a classical computers. So if I'm using a quantum system, then I can have some favorable overhead on a quantum system. So the simple metric would show like this. If I have a system, quantum system, 1, 2, 3, and if I'm just considering 2 levels of them, might be an outer level of chemical complex molecules or something, what is the number of classical qubits needed to just simulate some of those dynamics? So we can see that if I'm even looking at 30 or 50 qubit system, the number of classical qubits needed grows significantly high. I need about 10 to the power of 16 classical qubit system, classical bit system to simulate 50 qubit quantum mechanical system. So this is what when we say that a quantum simulators will help us in understanding quantum systems more efficiently than any classical computers do. And people are following a lot of approximation methods to deal with in the current scenario. And keeping this in picture is what we are looking at, simulating quantum systems. So there are 2 standard versions which has been followed to simulate quantum systems. One is a digital quantum simulator, where the standard approach is that you have, every system is defined by an Hamiltonian, and you are looking at approximating it, like you decompose the Hamiltonians into sum of local terms and approximate them with some discrete-wise unitary operators. And these are usually implemented or using gates on qubits. And that's one of the standard universal approach for digital quantum simulation. And the other version is an analog quantum simulations, where you are not trying to look at some standard universal approach. So there are some systems, Hamiltonians, which maps to another quantum system Hamiltonians with some approximation. And you try to pick those quantum systems whose Hamiltonians match, and then tweak around a bit of their dynamics and mimic the other system which you want to simulate. So this is called, these are analog quantum simulators. Cold atoms in optical lattice is one of the good examples for analog simulators to simulate some of the quantum mechanical or quantum condensed matter systems. So with these 2 standard approaches which has been followed for quantum simulation, so we try to focus on what is specifically needed to have a digital simulation. So my focus is largely on digital simulation. So first we need to look at the complex quantum system. It can be some system with environmental interaction, or it can be a many-body interaction systems. We need to come up with some quantum algorithms to have a good approximation of what the dynamics happens in that, and build a quantum circuit for that. Now the quantum circuit building also is a lot of, you have to look at what are the connectivities, or what are the ways you can mimic the dynamics of the algorithm. So there has to be some approximations goes from it. Identify and quantum hardware on which you can implement these gates. So I will try to pick a couple of examples which we are trying to work on and go through all of these 4 steps. Which means we try to look at picking up a quantum system, develop algorithms for it, come up with a quantum circuit, and also implement it on a quantum hardware. So for the way when I said here, there is a complex quantum system and you need a quantum algorithm. So one of the algorithms which have been focusing for the last many years is a quantum walk. A quantum walk is an algorithm resource for quantum simulation, just like the classical random walk has been. So a simple analogy between the quantum and the classical, the schematic would show, you have a classical random walker, we toss a coin, you move to the left or right, and it's a very probabilistic nature of finding the particle at some point. And the way the mapping of that to the quantum would be that the particle evolves in superposition. So it spreads in position space, and there will always be some superposition possibility of finding it at some point. So it means that there will always be some finite probability of reaching your destination. So this is a simple analogy of a classical and quantum walk. In a discrete version of quantum walk, you have a similar coin, which is like I talked about classical random walk head or tail. We take a two-dimensional particle with spin up and spin down, or it can be in superposition of that. So you can describe an initial state should be a superposition of two possible states, and then the coin operation would be an unitary operator, which brings it into any other configuration of superposition. And a shift operator would be in the same language like the way we do it in classical version, that head will move to the left, or tail will move to the right. In a similar way, your spin will move to the left, spin down up will move to the left, and spin down will move to the right. So you can have a shift operator which is of this form, which will evolve in superposition of position space. Now, the only difference is the unitary operator and evolving a particle in superposition of position space, and that does result in a significantly different output in the probability distribution. So a classical random walk gives us some distribution in this form, but a quantum walk gives you a bipodal spread in the position space, and that's mainly because of the unitary operators we are using and the interference of the particle when it's spreading in position space. Now this, more than being, this as a tool for simulation came a bit later, but in the initial days it was largely a quantum algorithm for search and various other applications, because the quadratic spread in position space found a huge importance in quantum search algorithms. So most of the best search algorithms today in quantum computing picture are based on quantum walks. It can be finding some points in your graph, or looking at some disordered dynamics, or even in communication protocols, people have been using quantum walks. So, but from looking at a simulation perspective, quantum walk can simulate localization effects, which are seen in condensed matter system. It can simulate the dynamics of Dirac equation, directed transport, and also topological insulators. When I'm saying that it can simulate, it means that there are experimental results which have actually used this algorithm and simulated them for the last few years. The idea of evolving particle in superposition came in 1986 by Feynman, and it has evolved over time with more input into it and operational approach for that. So one of the problems which we try to look at is a simulation of Dirac equation. If I'm looking at the standard Dirac equation, the textbook formalism of Dirac equation, we have an Hamiltonian, we have a derivative in time, position space, mass term, and the velocity term. Now, again, before the era of quantum information or quantum computing came, Wilson, Feynman, we all have looked at how you can simulate field theory in computers. When they were trying to look at, they came up with discretization approach. So the standard way of, if I'm trying to look at this time derivative and position derivative operator, I can write them in a difference operator form and come up with a unitary matrix for this Hamilton, for this Dirac equation simulation. So now, if I'm looking at this unitary 2x2 unitary matrix, it has a component which moves to the left, which means that you can look at the derivative in position space, and there is also a component which moves to the right depending on the spin of the particle. And there's a mass term here, or I'm writing this beta mc squared as beta prime. So there will be a component which moves to the left and right, and there will also be a component which does not move in the unitary operator. So now the quantum walk description which I said, you have a particle in superposition, it moves to the left and right. If I'm just writing that matrix in, again, a similar form, the way we look at Dirac's cellular automata model, it has the same form, but there is an off-diagonal term which also has shift operator. So which means that the particle moves to the left or right. So now there is some difference between the way Dirac cellular automata evolution looks and a quantum walk evolution looks, because this term doesn't have any evolution in position space, but this term has an evolution in position space. So now that making it a difference, how do we see it pictorially? If I'm looking at the schematic of it, a quantum walk evolution in position space, like because it moves to the left or right, there would always be, depending on odd or even time evolution, the opposite sides will always have a zero occupancy. And that's how it looks like. And that gives me a probability distribution of something like this. Now, the cellular automata model, the Dirac cellular automata model, there is an evolution which moves to the left and right, and there is also a component which is not moving, which is coming down directly in the same, or it's retaining the same position. Now, this results in some fine oscillations, which is not seen in a quantum walk model. And this people have find a mapping between this and Zitterbaum oscillation in Dirac dynamics. So now this is coming from the mass effect. Like if I have a massive Dirac particle, then the oscillations could have a big, different picture. But for some specific mass, it will be in this form. So now, when I'm looking at coming up with an algorithm for simulating Dirac cellular automata model, then it means that I need to modify my quantum walk algorithm such that I repeat this oscillation so that I will be mimicking the mass effect, and I'll be trying, I will be able to take that, convert them into a quantum circuit and implement into the physical system. So to make such kind of modification, then we have to see how do I tweak the quantum walk, standard quantum walk dynamics. So now this is the comparison of the regular walk and the cellular automata. But the way we can do is, instead of having a particle moving to the left and right simultaneously, we call it a split step quantum walk, which means that you break a single step of quantum walk into two parts, where a component stays at the same position, move to the right, and then another step, it will be a component staying at the same position, moves to the left. So which means that after every step, you will have a non-zero occupancy in all the three positions which it's implement at any given point. So now, which means that we are retaining the component to stay at the same origin and also moving to the neighboring position space. So now, if I'm just converting them into unitary matrix formalism, then I would just see that exactly the way cellular automata looks like, which means that there will be a diagonal terms where you have a particle moving to the left and right, and there will be off diagonal terms where you have a component which puts up at the same position. So now this is an exact mapping of quantum walk algorithm to a cellular automata model. Now the mass, I can choose theta values, some different theta values, and I can mimic the mass term, and I can mimic or change them as per our requirement. So there has been series of work from from starting from 1980s to latest in 2015 to 17. The theoretical models evolved over time, and now, since we can simulate a Dirac cellular automata model, we can look at all Dirac dynamics in it, and there has been various work which looks at localization, transition from localization to delocalization, and various others. One of the examples which I picked up would be to see to go to yeah.
Just one question. Sorry, maybe a very naive question. So your spread is ballistic, right? Even in the spread is ballistic, right?
Ballistic, yeah.
So is there a way to sort of control the spread
you can control
to diffusive and things like that, even in the quantum problem?
Yes, a lot of things can be done. So the way I can bring in a periodicity, I can bring in a disorder into that, and I can tweak around the spreading in the position space. So you can have a complete control over the spreading by changing two parameters. One, the initial state I begin with, and also the coin operators I choose.
I see.
So you can have a complete, even the transition, we have some work long back, it's like transition from, or you can have a combination of localized and delocalized wave packet also, using a quasi-periodic coin operations in sequences.
I see. But you can even have diffusive kind of.
Yes. Completely diffusive. Okay. So diffusive, one, you can make it diffusive by introducing noise. You can also make it diffusive even without introducing noise into the system. Both method can be brought into it.
Okay. Thanks.
So yeah, it's a single particle dynamics can be controlled in many ways. But what we are trying to look at was, okay, now how do I move from a single particle to a many particle or three particles? So one of the simple examples to look at three Dirac particle in mathematical structure would be a Newton oscillation. This is one of the standard textbook description for Newton oscillation. It's a very well established one. You have three flavors. with electron muon tau, and there is a flavor change which happens with the mass eigenstate. And so in the standard model, in the standard model of Newton oscillations, it was initially considered as massless, but experimental observations disagreed with it. Then there was a mass term which was introduced as a correction, and that did open up as a completely high energy physics beyond standard model. But that's not our interest. Our interest is try to see how I take this 3-flavor Newton oscillation and use this algorithm to simulate them. So which would kind of tell us I can simulate a 3-particle system in a quantum computer. So again, a standard textbook version of writing the Newton flavor in superposition of a mixing matrix and the eigenvalues of it. So I would have a unitary matrix which kind of can be broken down into some terms, and it will be spanned by 3 mass eigenstates. This is again a Dirac Hamiltonian. Right now, when I have a Dirac Hamiltonian, then I can always map it into quantum walk. So the propagation would be described by this, starting from time 0. How would it evolve in position space? And I can also compute a transition probability, because I mean the physics part of it is not not too important for us, because all that we want to look at is there's a unitary matrix and there are eigen values, and there has to be some operations on them which will allow me to have a transition probability from one flavor to the other flavor. But now the only takeaway information from us from the Newton physics description is there are 3 flavors and there is an oscillation between the flavors. Now I can see them as there can be a 3-qubit system or a 3-particle, and there is some kind of jump from one particle to the other, some information, or there can be some interaction. And the decrease in flavor in one will result in increase in the probability of one flavor to another probability of that. So in a qubit language or in the basis states, because it's 3 flavors, and each one would have 2 possibilities. So I will have 6 degrees of freedom. So okay, so 2 spin degree each for each flavor. So I can write them as a 6 possibility in this configuration, and I can consider as a 3 pairs which will simulate 6-state dynamics. So I can have 1, 2, 3, 4, 5, 6, and I can define an Hilbert space for them in this particular configuration. And an evolution operation, I can think of some evolution operator on each one of these space. So it can be a coin and a shift operator, exactly the way we did for a single particle Dirac equation. Now the difference between the single particle quantum walk or a Dirac equation is I have a particle and I have a position space for which it was hopping. But here I can actually think of a particle, and hopping is from one particle to another particle, which means that I can think of flavor change as a hopping component which comes from the shift operator. So we can define a coin operator on a 3-qubit system, which will map like I can pick a 3-qubit system, so which will be mapped to the 6 possible the flavors probability outputs which I'm going to get as my 6 eigen states which we can measure. So if I'm taking a 3-qubit system, it will usually be 8 possible basis state, but I just have a 0 operator for them. So these 2 are ignored. So I will be having the 6 possible basis state. A shift operator will be exactly like the way we had for a single particle. So now the basis for them, or the equivalent state for each flavor would be a superposition of the combination of these 3-qubit system. So now if I am doing a coin and shift operator of this form, the way we did for a single particle mapping into a 3-qubit system, depending on the way I define my theta operators, I can reproduce exactly what has been there in a standard textbook version of 3 flavors. You start from one flavor and then you see decrease in one, increase in the other. So both a short range and a long range oscillations can be exactly mimicked from a 3-qubit system. So now this kind of says that once you have a system, complex system, I can pick off an algorithm and try to map it to a system which we want to mimic and look at it. So now this is a stage of you are looking at a physical system and you have developed an algorithm and you say, okay, I have some algorithm which can mimic some 3 flavor or a Dirac equation or a 3 Dirac particle in some kind of configuration. Now, how do I come up with a circuit for it so that it can be implemented in a physical system? So the next step for us was to come up with a mapping, because if I have to go for a qubit, if I have to look at some hardware, then there are number of qubits, then the number of qubits, and there are position space, which we talked about. Now it's a one-dimensional quantum walk, for example, or like Dirac equation, which I'm looking at. So which means that I need to, if I have to evolve a particle in position space or a Dirac particle spreading in position space, I can choose a position space from -7 to +7. Then I can define the qubits basis like this. Now, how do we choose this basis? This is an optimization problem. We try to, this is one of the simplest version which we have come up with some optimization. There are mapping here, which means that I need at least a 5 qubit system to implement some 5-step of quantum walk or a Dirac equation. So there's a position space and there is a spin system. So now position space, 4 qubit will go for a position space. So we come up with some particular configuration, and if I want to move a particle from 0 to -1, then I need to have a qubit or the last bit flip from 0 to 1. So which means that I need to simultaneously go from 0 to 1 and 0 to -1, which means that I need to have a flip of this form and I to also evolve to this particular state. So which means that from here I need to evolve to superposition of this particular configuration. So for that, if I have picked with any initial state to come up with some quantum circuits, which would be like coin operator, again spin superposition on it, and then some control NOT gate. So now, if this is one of the versions of the circuit which we developed, and if I take this to any experimentalist or even to my lab and I see I have this circuit, and if I want to implement, then say, okay, this is too complicated because the number of control NOT gates you are using is very difficult, and probably we can't simulate them in a given existing system, even a few number of steps. So what people are looking at from moving from quantum algorithms to quantum circuits and implement in physical system is to come up with low depth quantum circuit, which means that identify the proper mapping and see, instead of having a very generic state for a given initial state, can I come up with a less number of quantum gate operations? And we came up with few where you begin with some fixed initial state. We know which initial states are, and then develop a circuit for it, like coin and shift operator with only less number of controlled NOT gate operations. And this is the circuit which we had for up to 7 steps. This is more complicated, but that's an example. So now this circuit was something which could be implemented in the existing quantum processor. So this is a processor in University of Maryland in Chris Munder's group. So we had some kind of iterations and exchanged optimization approaches, did some few rounds of optimizing a circuit, and then even to implement about 5 steps of Dirac cellular automata model. So we had to implement about 78 single qubit and 2 qubit gate. Now this is a very clean form of circuit which you are looking at, but if you are going to any hardware, the qubits are not always connected, or you can't directly take one qubit and do some kind of operations with any other qubit. So this in total there was an 8 qubit system. Some ancillary qubits were used to implement this circuit explicitly. So that's how the number of gates are very high. In fact, this number of 1 and 2 qubit gates are the best even today, looking at the coherence time available in the system. Even if I'm having about 50 qubit or 100 qubit systems, you will still only be able to implement slightly around this number of 1 and 2 qubit system in an existing, and even superconducting probably is not still up to that mark in terms of coherence time. You will have an access to large number of qubits, but not to the coherence time to implement gates. So this is the experimental and the theoretical results mapping with each other, and with very good efficiency we could get at this form. So now this is one simple, the neutrino flavor is one simple 3 qubit example, and the other one is again a simple protein complex which is very well studied. But what they talk about is that there is a directed transport, there is an environment which is affecting the dynamics, so which is called as environment tested quantum transport model, which describes the dynamics in FMO protein complexes. So there is some photon which falls on the site of the protein, and there is some particular path it takes and reaches the reaction center. So now there is a mix of there's what open quantum system approach. There is an environmental effect which is affecting, and there has been various models which has been developed to understand and then simulate them. So we can again come up with an algorithm for that. Again, I mean, it can be treated as if I'm only taking 2 sites and not the 7 which are there, we can always break them up into a quantum jump and then some noise effect, completely unitary evolution and the noisy effect units that would lead to a directed transport. So I'm not going into the details of the algorithm, but if I'm treating it as an algorithm like this, a mixture of quantum walk and the noise effect into that, I can simulate exactly what has been experimentally observed here. For example, if something falls, the photon falls on site 1, there is some particular route it takes to reach 3 or 4. And if it is, that's what the initial state, if it's something which falls on 1, it goes to site 3 after some time period. But again, if it falls on some other site, you are not going to see transferring, it will only be oscillating at. So now this model, when you try to write them in algorithm form, we will be able to change the energies and then control the environment and then study the dynamics beyond what is experimentally observed and also think of engineering. So we could look at environmental effect and everything, but now to again simulate them in a quantum system or in quantum hardware, I only need a 3-qubit ideally, because it's only a 7-site or 8-site system. I can prepare an eigenstate in a 3-qubit system, but I also need to mimic an environment. And the environment can be introduced by 2 more qubits to control the effect on them. So we have come up with a circuit which can be used to exactly simulate what has been observed experimentally. But the problem here is that it's not yet been optimized, or we have not been able to get it to the level where it can be executed in the existing quantum processors. But hopefully in a coming time, we can look at it. So all this is only a preamble to see how these circuits can be implemented in few other, probably even photonic system far better. So this is another example which we are trying to look at. Now, I would try to see, the whole talk was to come to photonic qubits, and this was only to say how you can build or come up with a protocol or algorithm for simulation. So we are trying to build a photonic processor using quantum walk itself as a primitive for it. And there has been various models for photonic quantum computing. So one is a discrete variable approach where you encode photons in different paths, frequency or time bin. There's also a Gaussian state approach where people create some kind of GKP states and then look at Gaussian operators. And there's also cluster states. People are using squeeze modes to come up with a measurement-based quantum computing and then hybrid approaches. But one of the most popular one, which it has come out in news, is boson sampling problem, where people have been able to demonstrate about 70 plus qubit of, or like 72 photons doing boson sampling. Now, boson sampling is nothing other than a multi-particle quantum walk in it. It means that you have many particles, and then you just let them interact in the position space, and then you get an output, which is classically a very hard problem to solve. But the mapping of that would be calculating permanence in a mathematical language, and that kind of says that even if you're not controlling, there is some specific problem which you can use as a many-particle quantum walk and do a boson sampling. But these are a very special purpose computation. It can't implement gate or anything. But the problem with this discrete variable approach or photons for quantum computing, though that was one of the first models which came, it didn't kick off as a promising hardware. It's because of the probabilistic nature of the gate operations in it. Because photons have bosonic behavior and they can't be controlled the way you want, and there are some specific ways. But there are various advantages, because photonic qubits operate at room temperature, they're robust against noise. And there are various number of ways we can encode qubits. At the end, I can use degrees of freedom. All that I need is an Hilbert space where I can access orthogonal basis. So the mapping can be done in various ways. You can scale them, and people have demonstrated high fidelity gates in photonic system. But there are other hurdles where, again, the most important is the interactions between them, and even creating a massive entangled cluster state. But the way we wanted to approach was, can I make the photonic qubit operations less probabilistic, or can I make it deterministic up to some point and then bring in probability at a later point? And that would resolve the problem of the probabilistic nature of photonic qubit. And for that, there has been some approaches or proposals, theoretical proposals, more than a decade back. But they didn't evolve into a physical architecture. It remained a mathematical models. But if you are looking at, when I was talking about the way we implemented quantum walk on an ion trap system, or the way we mapped was, we took a many qubits and then we mapped them into a position space. So now if I do a reverse problem, which means that I take a position space and I map them into a qubit, then I can realize a multi-qubit system by a walk itself. So which means that I take a particle and I put them in a tensor product in a position space. So then I will be realizing a 2-qubit system. Now I take a particle and I put them in a tensor product of a square lattice, then I can realize a 3-qubit system. Of course, the problem does not scale because 2 plus 2 and 2 to the power of 2 are the same. So the scalability problem won't come in here. But at least it brings in an idea of how you can make the particle walk in position space and implement gate operations. So again, the coin operation and the shift operator, which I talked about, is now bounded to a 2-position space or a square lattice. The universal set of operation would be coin shift in some different configuration. Like it can move to the left, remain at the same position, or move in superposition. We can pick a class of them. And I can, if I'm looking at a 2-qubit operations, I can always have an Hadamard operator on a first qubit, which means that you just do a rotation on them. And a second qubit, it's a combined effect on both the position space. I can implement all the phase. Mathematically, it looks quite sound. For a control not gate operation, it means that I just have to swap the positions, like I move from here to here and move from here to here, some particular states. And for the reverse control not, it will be identity operator in one position space and sigma x on the other space. So one can even look at all 3-qubit operations at Toffoli gates and control not gates just by looking at the shift operators. You don't even need coin operations if you look at here, because these, in a standard superconducting or any other quantum computing architectures, doing an higher number, like an higher order controlled gates are very difficult. But if I'm trying to look at a walk model, it's only a shift operator. I need to know how I transfer the state from one particular position to other position. Then I'll be able to do a multi-qubit controlled NOT gate operations with good efficiency, right? That's something which the model had promising approach. You can scale with a single qubit in some tensor network, a single particle in a lot of position space, and build an n-qubit system. So it remained a mathematical framework. Now, how do I convert them into the physical system? And that's something which makes the most important part of the work which we are trying to look at in our lab, is that now I need to have a particle. I need to have an access to position space. So what is a particle for me? I'll begin with a photon. And my position space will be there for the photon to move in any given. So the way we generate single photons or even entangled photons, I mean, you take a laser, there is some nonlinear crystal, it passes through it, and then 1 in a million photon converts into 2 photon by down converting, which means that it converts into 8-10 photons of 2. And most of the photons don't convert and we just throw them out. Like 405 would just remain 405 and passes through. But 1 in a million creates a pair, and these 2 pairs come up in some particular. But this is a long exposure shot. At any given time, there will be photon in one ring and another photon in another ring. It comes with, I mean, I can use different kinds of crystals. They are available. The technology or the technique has been standardized over like last many decades. So there are PPKTP crystals and there are like BBO crystals. This one, it can give me light in this particular configuration. I just have to pick an exactly opposite points in the position space, and these 2 photons will be entangled. Anything which we see in these regions will be entangled. Or if I have this configuration, nonlinear rings, then these 2 photons will be entangled, which means that because of this overlap region, there will be 1 photon here. If it is H, the other one will be V. And if this is H, the other one will be V. So now that gives me a way to generate single and entangled photons. But I'll just focus on a single photon here. Let's not worry about entangled photon pair, which means that when I say single photon, it means that I'm only taking photons coming in this one ring. At any given time, there will be 1 photon horizontal. And if I'm splitting, or like if I'm separating these 2 rings, I can actually spatially bring them into 2 different points, which means that there will always be 1 photon in this ring and another photon in this ring. So now that's something which we kind of pick only 1 photon and entangle them in polarization and part degree. So the way, it's a coin operation. Again, simply, I know I can have a photon, I do a waveplate rotation, which is like changing the polarization into superposition of some combination. If I have an horizontal photon, then this will bring it into superposition of horizontal vertical polarization. Then I can split them into 2 paths. they're using a polarizing beam splitter. This is just a two-step quantum walk. You know, I'm doing a coin operation, shifting in position space, coin operation, shifting in position space. Now, if I look at the output here, I would have 4 possible outcomes. And this is, it means that I will have to have 4 detectors to measure, and I will have 4 possible measurement output, H0, V0, and then I would have, again, I mean, H1, V1 as the configuration. So I can choose the 4 possible measurement outputs. And yes, yeah. So that all 4 basis space can be generated. So which means that it will give me, this is the Hilbert space dimension. So I can create a 2-qubit system out of this with a single photon. In the mathematical language, it is only a tensor product of polarization and part degree. And my measurement output will be all 4 possible basis states which I would get. So now, how do I show that this is really entangled? I mean, I can always have it's a photon coming out from a beam splitter, and then there will be 2 output. So it's a superposition, and why are you calling it an entanglement? And that's the question which would come. But now, if I'm seeing it in a picture of a 2-qubit system, all that I should be able to establish is that I will be able to measure all the basis states in all orthogonal configurations of them and show a Bell's violation for that. So which means that I need to have a control over, I need to change the angles in one and the other in various configurations. It means that there will be 2 Hilbert spaces here, particle and the position. It means that I should be able to have H, V, and access to diagonal on the photon degrees of freedom. And I should also be able to, I have a control over what would be the probability of finding the photon in all these 4 parts. So it is 2 Hilbert spaces for me. It's the H polarization and the part degree. And I can show a violation of Bell's inequality. Theoretically, if you just write down and what should be the rotation, we'll be able to find out the angles of these rotations for which we can show violation of Bell's inequality is about 2. And then this is the theoretical prediction, and experimentally we could get the violation of Bell's inequality and establish that it is a 2-qubit system. And this is not something which we have explicitly looked at it. People have also studied more complicated. It means that they have taken polarization, path, and time degrees of freedom. So the highest number which has been reported till now is using a 6 photon and 18 qubits in polarization, path, and time bin. So 18 qubit GZ state has been demonstrated. But this is the simplest version of that, because time bin we didn't want it to include because complexities are involved, which means that I need to put this photon in loop and also have a precise measurement of the time. But this kind of gives us a simple way of having a control over the 2-qubit system, split them, and because the polarizations H and B don't interfere, it doesn't matter whether they come the same output or I can split them in position space. So we thought this 2-qubit can still be of some use to generate random numbers from that. So the first application of a 2-qubit system without even implementing gate is, it shows that I use single photon and generate 2 bits. So that itself was something which is kind of interesting, because the earlier demonstrations which people had tried to look at was use single photon and generate random numbers, which with each photon you only get 1 bit, but because we are converting it to 2-bit and then I have multiple detectors, we could get large number of bits compared to the one which was reported earlier. And there's a small device which we tried to build from that 2-qubit system in our lab. Now that's just a precursor for it. Like, now I can't create a 2-qubit state. How do I implement gate operations? So we had to come up with the framework for it. It took quite a bit of time for us to develop the whole model. And if I have to implement, now this is just the 4 path I have. If I have to implement an Hadamard operation on the first qubit, because of photon, I just have to put a waveplate and rotate them in some particular configuration. But if I have to implement an Hadamard operation on the second one, which means that I have photon coming in 2 paths and both of them are my second qubit, I need to make the single photon interference to have an Hadamard operator in the second one. And these photons are like 810 nanometer wavelengths, and the path length has to be matched precisely to that wavelength, because it's actually a single photon being in superposition and interfering. So these are the theoretical scheme for implementing Hadamard on the first qubit, second qubit, and even the control not gate. And these are our experimental results, which we measure by doing a tomography, which means that you get this output and then you access all the 36 measurements we had to do to reconstruct density matrix, and then find out what is the fidelity of it. So we could do that. It took quite a lot of time. But the interesting thing is that implementing Adamant on the second is slightly difficult because even if it's on the second qubit, you are involving two paths and you're making them interfere. Single photon interference has to be very precise. But implementing a control knot is a lot more easier because depending on the polarization, you have to change the path. This is not an interference here because a polarizing beam splitter, not a standard beam splitter. So which means that it's a swapping of the paths. It becomes very easier to implement control knot gate. And these are the other all standard 2-qubit gate operations we have implemented in our lab, where your phase gate on the first and the second qubit. This is the standard model, and how we use quarter wave plate and half wave plate combinations to implement phase gate. And on the first and the second, you need to, this is a kind of introduce a path matching. You have to introduce some crystals so that the path length matches. Because sometimes H and B polarizations, there will be some delay in the way the photon comes. And this is a control from second to the first control knot gate. The fidelities we could achieve. In fact, this first time demonstration of many of these gates in polarization part degrees of freedom, even the 18 qubit which was reported using 6 photons, they only created GSZ state and they did not demonstrate the gate operations. So, but this numbers are quite promising and good. I mean, achieving 97, 98, 97 or 96% fidelity in room temperature setting is something very promising with the photonic qubit system. So in the interest of time, the 3-qubit also a complete architecture of how we can implement, because now how do I go for 3-qubit? It's a single photon and part degree. I need 4 paths and then a single photon in polarization degree, and I can encode a 3-qubit system, and we can implement the control knot gates in all of them. And there's a small unit of in our lab where we call it as a 3-qubit module, where you send a photon and then you have paths for them to go. So that makes a single 3-qubit unit, can link it up. So we kind of, what is the usefulness of, I mean, can we come up with some simple use cases for 4, 3 or 6 qubit systems? So one thing which we recently reported was, if I create a 4-qubit in the same way, like I have now, scaling is a problem, which means that if I want to make 5, 6, 10 qubits, I can't have too many paths. And the moment I'm putting in large number of path degrees of freedom, things becomes more complicated. The way we have tried to resolve them is that instead of taking single photon, I take 2 photon. Now 1 photon goes and creates a 2-qubit here with polarization part degree. The other photon goes and creates a 2-qubit here, polarization part degree. But the entanglement between the 2 photons which has been generated here will entangle these 2 qubit and these 2 qubit, and we could generate any arbitrary 4-qubit state, which pick one specific state which can be used for generating public and private key, and we demonstrated how 2 qubits can be used to send across 2 parties and then use them as. So 6-qubit state is an example of how we can generate a 6-qubit state. I have an entangled photon, 2 photons coming here, a 3-qubit module and another 3-qubit module. And now the standard way for generating GSZ state has been known is like you put an Adamant on the first, control knot gates. But here I have a photon which are entangled here. So which means that first and the 4th qubit are entangled in the beginning. And then I do a control knot gate. Now this will give me an exact GSZ state output. Now to get a GSZ state, a 6-qubit entangled state, which means that if I'm looking at the point here, which means that this is a 0, 0, but this is a polarization degree, which means that I should have only one polarization here and only see photon in this path. And here it should be 1, 1, 1. So which means that I should be able to measure photon in this path, this, and this path. So there will be only 4 paths where I should be able to measure photons, and then should not get photons in any other path. And we have, this is an experimental verification, output verification, what we call a visibility test, which means that I will, to make sure that they are really GSZ state, I can change the polarization here and get a visibility, which means that the probability of finding photon, the moment I change the polarization of the first to some diagonal basis, then it should shift, and it shifts, and this was about 98.5% accuracy, and the other one is about 96%. So it shows a very high fidelity GSZ state generated from the system. So now we have been able to implement 3 control knot gates and an Adamant on the first qubit. So this 6-qubit system, there is a gray coding methods or few other approaches of mapping a standard circuit to our architecture. So using some of those examples, we can always generate more complicated or more desirable 6-qubit system, and we are trying to look at it can be an FMO complex, which I described, which only needs a 3-qubit system or 4-qubit system with the environment effect, and another model which we are trying to, we have now converted our algorithm to the one gates for our architecture, and we are now started looking at how we can implement in our 6-qubit system. And this kind of gives us a starting point to look at simulating many body systems, because all that we wanted was to try to at least generate few controllable qubits and think of some smaller number of many body systems, or like like a 3 or 4 particle systems, and do some mapping and look at it. Might be in the coming years we'll be able to look at it. There's a lot of contributions from various people. The list is very small here, so only I picked up my former students who did theoretical work developing quantum computation model to simulation protocols, and my current students who are working in the lab doing experiments, some postdocs who helped a lot to set up the lab, and the collaboration with Chris Monroe's group, where we worked with ion trap, really set us an example, see how we can do an inverse mapping and then build a photonic architecture, kind of gave us a strong confidence that experimentally we can do the inverse mapping and look at it. And the funding for the lab is currently from the Office of PSA and been generously supported to build the setup which we have. Thank you very much.
Unfortunately, we've gone past time a little bit, so maybe we can take one or two.
Trying to understand like how you manage to get like this kind of Bell's inequality measurements in with a single photon. So like, for example, if you have a single photon on 4 sides, like the first 2 sides you might think of up and down, and if it's on the last 3/4 you would think of up. Right? But usually, like you have to take 2 spins. The usual Bell experiment, you have to take 2 spins far off and then make simultaneous.
No, I get your question. So the way we so now what you are talking about 2 particle, there is a basis states for me, and then for 2 particle to do the Bell's violation, I know what are the basis I need to measure. So that's what for the standard 2 particle system which we have. Now, if I'm mapping it to polarization part degree, I write down the basis of the part degree and I exactly still have a mathematical structure. Now, in that mathematical structure, what are the basis I need to measure? So it will always be a combination of polarization path basis I have to measure, and then those are the values which will be used as an input for me to show the violation of Bell's inequality. Now here, there is one other fundamental question which people have been debating, and there is like, does such kind of Bell's inequality in a mathematical structure is establishing non-locality? And this is a question which people have come up with, how you can actually show violation or non-locality with a single particle in an experimental scheme. And we also have tried, and we also have another experimental setup to verify that non-locality. All that we need to show is that you have a single photon split in many paths, and some interaction one path should affect the output on the other path. So there are few models which is there, and that is an ongoing debate. Now, the way we are approaching this problem is in terms of resource here. For me, it's a mapping of a 2-qubit, and as a resource, it's serving the purpose. But the profound questions of non-locality of single particle are, experiments have been there, they have been debated, and more experiments are in the progress.
Right. If there are any more questions, maybe we can move them to the coffee break. So let's thank our speaker again.
Thank you.